Now, I'm going to give you a heads up. This first part of chapter 13 is probably the hardest thing we do in FST, or at least in FSTB. For some people, chapter 8 was harder. Chapter 8 is always its own beast, and it depends upon how you do with factoring. But the beginning of chapter 3 tends to be one of the hardest things we do in it. So there are some things that I do at the very beginning of FST, which we'll talk more about next week, that are just, or sorry, at the very beginning of this chapter, I meant to say. There are some things that I do that are going to be a little bit different than normal when it comes to things like homework. But that'll be next week. Most of what you're going to see is going to be similar to how I kind of structured things before. Because the beginning of chapter 13 focuses in on the idea of trig identities. Does anyone remember what an identity is from a previous class? And just to be clear, I expect the answer to probably be no. I expect the answer to be no because most of the time the actual term identity gets kind of overlooked. So, identities that you would have learned in previous classes are things like this. The multiplicative identity is the number 1. The additive identity is the number 0. And essentially what an identity is, it's an equation that's always true, regardless of what variables go into play. Multiplying by 1 is always going to leave you with what you had in the first place. Adding 0 is always going to leave you with what you had in the first place. Trig identities, specifically, is a trig equation that is always true. Specifically, it is always true provided it is within its defined values. It is not true in situations where you have something that is undefined. It has to be defined. It has to fit within its domain. We already know some trig identities. We have the reciprocal identities. These are ones that we've actually been working with throughout all of trigonometry. We just haven't necessarily called them identities. It's this idea that sine is the reciprocal of cosecant. And that cosine is the reciprocal of secant. And that tangent is the reciprocal of cotangent. Or, more specifically, we worked with the other 3 reciprocal identities because typically we wanted sine, cosine, tangent because they're easier to work with. More commonly, we dealt with the fact that cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and last but not least, cotangent being the reciprocal of tangent. These identities are not new, but it's been a bit since we've written them out this way for these three, and I don't think I ever wrote these three actually out that way. But knowing that they can be written this way is going to be hugely important in chapter 13. We have also used what is known as the quotient identities. Now the reciprocal identities, those come out of how trig is defined. Those come out of the fact that sine is defined as being the opposite divided by the hypotenuse on a right triangle, and cosine is adjacent over hypotenuse on that right triangle, tangent opposite over adjacent, and the other three being hypotenuse over opposite, hypotenuse over adjacent, and adjacent over opposite, respectively. The quotient identities also come out of this idea of working with a right triangle. But these ones aren't just based on how it's defined. These ones are actually created from manipulating what we know on the right triangle. So if I have a right triangle in which I'm referencing an angle theta and side lengths of said triangle are A, B, and C, where A is the opposite, B is the adjacent, and C is the hypotenuse, then we should know that sine of theta is A over C, and cosine of theta is B over C, and tangent of theta is A over B. Now the quotient identity, these are not the quotient identities. These are just facts about that right triangle, given how I have set it up. The quotient identity says that I can find a trig identity by dividing some trig identities that already exist. Specifically, if I take sine, which was A over C, and divide it by cosine, which is B over C, how do I divide fractions? Multiply by the reciprocal, keep change flipped. So I get A over C getting multiplied by C over B. To multiply, I can multiply straight across, or I can simplify before I multiply. What's going to cancel out? C, and I'm left with A over B. Therefore, this was sine, this was cosine, and it turns into tangent. We have this quotient identity written on the bottom of our unit circle. That is one of the two quotient identities. The other quotient identity comes out of the fact that I can divide in a different way. I can divide cosine divided by sine. Now I've talked about what cosine divided by sine is going to become. But which trig ratio is a result of cosine getting divided by sine? Cotangent, because it's the reciprocal of this. Today, the only new identities to us that we haven't seen in some semblance are actually, or specifically that we're introducing today. There are an infinite number of trig identities. We in this class are going to use, if I remember correctly, it's 39 of them. So far we've got 8 of them. But the only ones we haven't seen so far that I'm introducing to you today are known as the Pythagorean identities. The Pythagorean identities come out of working with an angle in standard position on the unit circle. Okay. Those are some words, we've heard all of them before, but let's remind us what they mean. What's it mean for an angle to be in standard position? Oh, we should know this. Does not mean it's on the unit circle. It could be on the unit circle. It does not mean it's on the unit circle. What's at 0 degrees? No, a 0 degree angle is not necessarily an angle in standard position. Is that an angle in standard position? No. In standard position depends upon the position, depends upon the location of the angle. An angle in standard position must be located where? Not just in anywhere, it has to be on a XY axis with a vertex where? This piece goes where? 0, 0 at the origin. Now if I draw on an XY axis, now is that an angle in standard position? Yes. Is this an angle in standard position? No, because what else must be true? Positive x-axis must be one of its rays. So, angle in standard position, vertex at the origin, one ray is on the positive x-axis. It's all of the angles that are on the unit circle, but being on the unit circle does not make an angle in standard position. I think I said that backwards. So, we're going to just focus in on the first quadrant of the unit circle. What is a unit circle? It is on the green sheet, but that's not what makes it a unit circle, just being on a green sheet of paper, shockingly enough. It is a circle defined to be a circle of radius 1. We just happen to put it centered at the origin because that's the most universal way we can look at it. But it is defined to be a circle of radius 1. So if this is part of my unit circle, the part that's in the first quadrant, and I draw an angle there in standard position. There we go. There's my angle. And a little theta right there. If I wanted to do trig with that, if I wanted to figure out what sine, cosine, tangent, cosecant, secant, or cotangent was of that angle, I would look at what in reference to that angle? How do you find cosine, sine, tangent, cosecant, secant, or cotangent on the unit circle? What do you look at? The x and y, the coordinate point where it intersects. So we got that x value and that y value. What do you know about the x and y value in pertaining to the trig ratios? X is cosine. Y is sine. Now, this is called a Pythagorean identity that I'm trying to get towards. There should be a key word there that screams at you. Pythagorean. If you see Pythagorean, what should you be thinking about? A squared plus b squared equals c squared. Only applies to what? Right triangles. There should be a right triangle going on here. Ta-da, there's my right triangle. On this right triangle, I know it's hypotenuse. I know it's hypotenuse because The hypotenuse is the distance from the origin to the unit circle. The distance from the center to the edge of a circle is its radius, and the radius of a unit circle is 1. I also know its horizontal side length, at least in terms of trig, because its horizontal length is its x value of that coordinate point. That's cosine of theta. The height of the triangle, sine of theta. A squared plus b squared equals c squared relates the side lengths of triangles. According to this, if one leg is cosine and the other leg is sine on a right triangle, then I should be able to do cosine squared plus sine squared equal to the radius squared, which is 1 squared. This is not the traditional way to write an exponent on trigonometry, by the way. If you do it without the parentheses, you're only squaring the angle, which is not the same thing. So, one of the ways that they write out trig to some power is they put the power directly on the name of the ratio. And what is 1 squared, by the way? 1. The first of the Pythagorean identities is cosine squared plus sine squared is equal to 1. This came up on one of your homework assignments. This identity. Now, that's one of 3 Pythagorean identities. The other 3 Pythagorean identities work with the other trig ratios. They work with cosecant, secant, cotangent, and tangent. The way that the other 2, there are 3, that's the first one. The other 2 are created is by manipulating this one. You start with the identity that we know, cosine squared theta plus sine squared theta is equal to 1, and we manipulate it around to get the other trig ratios. How we do that is using the quotient identities. Let's say I want to get tangent involved. According to the quotient identity, tangent is sine divided by cosine, which means if I want to get tangent involved in this, here's my sine, I want to get it divided by a cosine. But a couple things I have to keep in mind. First off, that sine is squared, which means I don't want to just divide by a regular cosine. I want to balance it. I want to divide not by cosine, but by cosine squared. And if you divide one thing in an equation, you must divide everything. So that means this is also getting divided by cosine squared, and this is also getting divided by cosine squared. What is cosine squared divided by cosine squared? They cancel, leaving me with what? 1. Because they're canceling by division, and when you divide, you cannot get 0 unless it's 0 divided by something. The sine squared divided by cosine squared. Sine divided by cosine is tangent, which means sine squared divided by cosine squared is going to be tangent squared. And then I've got 1 divided by cosine squared. Now 1 is in itself a perfect square, so I could have written that as 1, or I could have written it as 1 squared. Why do I talk about that? Because in order to work with that, I have to recognize what 1 divided by cosine is. 1 divided by cosine, look up at your reciprocal identities, is secant, which means 1 squared divided by cosine squared is secant squared, and 1 is 1 squared. This is the second of the Pythagorean identities. The third Pythagorean identity also gets built in a similar manner. Cosine theta plus sine squared theta is equal to 1. I start with that. Enjoy your lunch. I've got a Pythagorean identity that has cosine and sine. I've got one that's got tangent and secant. The last one has cosecant and cotangent. Similar to how we got this one, we're going to build off of the quotient identities. We already got tangent, now we get cotangent. Cotangent's cosine divided by sine. What do you think I'm dividing by in order to get that to happen here? Not just sine, but sine squared. Cosine squared divided by sine squared is cotangent squared. What is sine squared divided by sine squared? 1. What is 1 divided by sine squared? Cosecant squared. Now, I purposely show you where these trig identities come from because of the fact that if you do end up choosing to go on to a higher order math, you end up going to, say, a calculus, you aren't just given these identities at all times. You're expected to know some of them. If you can know some of the basic ones, you can get to the other ones. If you know, like cosine squared plus sine squared equal to 1 gets used a lot in those higher order math classes. If you know that one, you can come up with these two by just recognizing how you get there. Tangent, we should know, is sine divided by cosine, but is it hard to get to that cosine or cotangent's the reciprocal of that? Shouldn't be. And then the reciprocal identities are ones that we should know. That being said, that is not the purpose of today. I'm not trying to get you to come up with the trig identities. Today you're going to see a couple of different types of things that you're going to use these trig identities for. Oh, and I maybe should hand this out for you guys. An entire sheet of trig identities. We will be introducing all of these throughout the chapter. Today we're focusing in on those 3. Don't get too caught up in the other ones right now. So, today you're going to see problems that do stuff like this. Find the exact value of. And then it'll give you some more information. Like find the exact value of cosine of theta if 90 degrees is less than theta is less than 180 degrees and sine of theta is equal to 1/4. There are 2 common ways to do a problem like this one. I have sine and I want cosine. So, one common way to do this is to look for the trig identity that relates sine to cosine without needing another trig identity to work with it. Which of our trig identities that we brought up today has sine in it, has cosine in it, but no other identities? These are the ones we brought up today. Which identity has both sine and cosine, but no other identity, or no other ratio? Quotient has another trig ratio. It's got either tangent or cotangent. Pythagorean identity. Sine squared plus cosine squared is equal to 1. So, 2 ways to do this. I'm going to show you both. So I'm going to break things down the middle. You don't have to know exactly how to do both. You have to find which way works best for you. First way, using that Pythagorean identity piece. In this case, the identity is cosine squared plus sine squared is equal to 1. So, cosine squared plus sine squared is equal to 1. I'm looking for cosine, I know sine, so I'm going to plug in what I know. This is still cosine squared theta because I don't know it. Instead of sine squared theta, I'm going to write 1/4 squared equal to 1. What is 1/4 squared? Nope. Nope. How do you square a fraction? Square the top, square the bottom. What's 1 squared? What's 4 squared? 16. I kind of figured you had the right idea of what you were trying to get at, but yeah. Okay, I'm trying to solve for cosine squared. What am I going to do? Subtract the 1/16 to the other side. Now, if I want an exact value, do I want to get decimals involved? No. How do I subtract fractions? Common denominator. Okay, 1 is currently 1/1, also known as, with 16 as its denominator, 16 sixteenths. 16 sixteenths minus 1/16. 15 sixteenths. To get rid of a squared, you take the square root. When you introduce a square root, what better be going with it?
The square.
When you put a square root on something, you're also supposed to put something else in front of it. Positive and negative, plus or minus. On this side, we're left with cosine of theta. How do you square root a fraction? No. Square root top, square root bottom. Square root of 15 is square root of 15. Square root of 16 is 4. So I get a square root of 15 over 4. Simplify the square root of 15 if you can. You can't. It doesn't divide by any perfect squares. This is not my answer. It's almost my answer. Cosine doesn't have 2 values. It only has 1. That plus or minus needs to be taken care of. Do you notice earlier that it told you where on the unit circle the angle needed to reside? Between 90 and 180. You got a unit circle, right? Grab it if you don't have it out. Unless you've got the entire thing memorized to where you really want to work off of memories for it. Look at the unit circle within the range that told you theta resided. And tell me, is cosine positive or negative in that range? Between 90 and 180, we're in the second quadrant. Cosine is what part of the unit circle? The x values. Are the x values positive or negative? Negative. Cosine should be negative within that range. This is one way to do a problem like this. I'll be honest, it's not the way I do it. I do a way that avoids the fractions. Do y'all want a way that avoids the fractions?
Yes.
Okay. Way number 2. Do it the way we did it back in chapter 12 because we've had problems like this before. Back in chapter 12, all the way back in 12.1, this was one of the first things we did. I gave you a trig ratio and said, tell me the other. Now, at the time, I told you the angles were acute. That was the only real difference that we did back in chapter 1, because we hadn't yet discussed the unit circle. And we used a right triangle. We drew ourselves a little baby right triangle called one of the angles theta and said, I know sine of theta is 1/4, and I also know that on a right triangle, sine is what over what? Opposite over hypotenuse. And therefore, on this right triangle, if this is my acute angle theta, I labeled the opposite as 1 and the hypotenuse as 4. If I want to find cosine, I need adjacent divided by hypotenuse. So I need the adjacent. I know 2 sides of a right triangle. How do I find the third? Pythagorean theorem. 1 squared plus 4. Nope. Try again, Benson. Get it straight. In Pythagorean theorem, a squared, b squared, c squared, which of those am I picky about? A, b, or c? C better be that hypotenuse, so don't do what I just did. I'm going to call that x. So, and let's try this again. 1 squared plus x squared equals 4 squared. That's 1. That's 16. Subtract 1 and I get x squared is equal to 15. To get rid of a squared, I take the square root. When you introduce a square root, you better put a plus or minus on it. Now, if this was a real right triangle, would we have a positive or a negative? It would be positive. Is this a real right triangle that existed? No. So we're going to put the positive or negative on it. And then we'd say cosine of theta is equal to the adjacent, positive or negative square root of 15, over the hypotenuse, 4. And then guess what? You can't keep both the positive and the negative answer, so what would you do? Check the unit circle for the range. You do that piece the exact same way. And between 90 and 180, shockingly enough, cosine did not change. It is still negative. These two ways are not all that much different. Both of them are built off of Pythagorean theorem. One just is going to get you the fraction in Pythagorean theorem. The other one's going to avoid the fraction in Pythagorean theorem. Either way, they work. This way's great if you forget to make a right triangle. Otherwise, I prefer that way. Y'all have a preference? Some people know. Some people prefer number 2 just because they really don't like fractions. Now, here is a big advantage for way number 2, though. A huge advantage for the second option is when I ask for something like secant theta, given cosecant theta. There's not a direct relationship between secant and cosecant in the Pythagorean identities. If you want to go from cosecant, or to get to secant, you have to go from cosecant to cotangent, because that's the Pythagorean identity that has cosecant in it. And then once you have cotangent, you have to go from cotangent to tangent, because the Pythagorean identity that has secant in it has tangent in it. It's a pain in the butt. It works, but it's a pain in the butt. Which is why I prefer doing the right triangle option. I'm told cosecant of theta is equal to a negative 7/2. Cosecant's a reciprocal of which one? Sine. So if I know that, then that helps me know that sine of theta is negative 2/7 and sine is opposite over hypotenuse. Now, I got a negative right here. How do you get a negative via division? I have to have one positive and one negative getting divided. It could be a negative divided by a positive, could be a positive divided by a negative, which means that negative could go either on top or on bottom, which could mess with our triangle. Or just avoid the negative altogether. Ignore the negative when you're doing this. You don't actually need it in the triangle. What you need is the numbers to get the third number, and then you do positive or negative based on this angle range. So leave the negatives off. Opposites 2, hypotenuse is 7. If I want to find secant, I need cosine, which is adjacent and hypotenuse. So I need the adjacent. If I know two sides of a right triangle, how do I find the third? Pythagorean theorem. X squared plus 2 squared equals 7 squared. X squared plus 4 equals 49. X squared is equal to 45. To get rid of a squared, I take the square root. X is equal to a positive or negative square root of 45. Simplify it if you can. Yes, 45 divides by what perfect square? 9. It's 9 times 5. So it's positive or negative 3 root 5. I want secant. We've generally started with cosine when it comes to right triangles. Cosine's the adjacent divided by the hypotenuse. To go and change it over to secant, flip it. Secant is 7 over 3 root 5, and generally the positive or negative goes out front. Am I done?
No.
I should not have two answers. So I look at the unit circle for angles between 3 pi over 2 and 2 pi. Which quadrant of the unit circle is that? It's the fourth quadrant. Secant's not directly on the unit circle, but its reciprocal is. Is cosine positive or negative in that quadrant? Positive. When you flip a fraction, does it change it from being positive to negative or negative to positive ever? No, it just flips it, which means if cosine is positive, secant is also positive.
We can just keep the square root on the bottom. Is that a yes?
Oh, I'm just having a day.
Why do you show up for class? We should just take a
Here's the thing, we were supposed to get through significantly more today than what we did. So, that's why I'm distracted. Okay, how do I simplify this? Multiply both top and bottom by square root of 5 in order to rationalize the denominator. I get 7 root 5 over 3 times 5, or aka 15. Can I simplify that? Nope. That's my final answer. Okay. There's one more example I am going to show you today. We're going to figure out what today looks like. Do you notice how little room I'm writing it in? Do you notice I'm writing in like practically no room left on my paper? You don't need a whole lot of room for this one, I promise. When you come across these problems, there's one key situation you should look out for that's going to make your life a lot easier. I'm looking for cotangent, I'm given tangent. What's the relationship between cotangent and tangent? It's not opposites, it's reciprocals. If I give you a trig ratio and I ask for its reciprocal, don't go through the work of making the right triangle. You don't need to. Just flip it. You don't even need to look at the unit circle for the positive or negative piece. Because if tangent's negative, guess what? Cotangent's going to be negative. Okay. We're going to stop right there.